In the next section, we're going to talk about oxidation-reduction reactions. These are also called redox reactions. I think because if you took ox and red and put them together, ox-red reactions would sound weird. Personally, I think redox looks a lot like redox, doesn't it? But it's redox, not redox. And it's not redox either. But it's just short for oxidation reduction because that's way too many syllables. So redox reactions are things that we observe in everyday life, although you probably didn't recognize them as such. If you have ever seen iron rusting, that's a redox reaction. Bleaching your hair is a redox reaction. If you've ever used a battery, and I'm thinking most of us have a battery in our pocket right now, right? In your cell phone, there's a battery. There's redox reactions going on in your pocket. And there's actually some going on in your brain as well. Many, but not all of those types of reactions are going to involve the reaction of a substance with oxygen. And so we're going to learn how to recognize these reactions. Here's two examples. When iron rusts, we have solid iron. The element reacts with oxygen gas and forms iron oxide. The iron oxide does not have the same physical and chemical properties that the iron does. It's a solid, but it's not as strong as the iron. And so eventually, like my old Mustang sitting in front of the house is, slowly disappearing. It's rusting away, right? Another example of an oxidation reduction or redox reaction is combustion, burning. So natural gas is primarily methane, which is CH4, and that reacts with oxygen and forms carbon dioxide and water. So when we see a combustion reaction, that is also an oxidation reduction reaction. So we need to understand the definition of oxidation and reduction. So oxidation is when a substance loses electrons, and reduction is when it gains electrons. And there's not a whole lot of sense in those terms because they actually came from a different sort of definition, and that definition made sense, but that's more organic chemistry, and we're not going to go there. So we have this helpful mnemonic, oil rig, that can help you keep these two things straight. Oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. And to this day, I still say this in my head. I'm looking at something, okay, it lost electrons. Oxidation is loss. Okay, that's oxidation. That's how I remember it. It works. Come on. There we go. So oxidation and reduction have to happen together. You can't have oxidation without having reduction. There are electrons being transferred. If one substance loses the electrons, another substance has to gain the electrons. We don't have electrons just floating around randomly. If something gains in electrons, those electrons had to come from somewhere. Something had to lose them. It's a little bit like money changing hands. If I take money out of my wallet, somebody else is going to end up with it. Even if I didn't necessarily hand it to them, if I just left it on the table, somebody's going to gain some money, right? Because they're going to see it and they're going to pick it up. So they always go together. Right now, the goal is to be able to identify redox reactions. So if I give you an equation, you should be able to say, yes, that's a redox reaction. So here are the guidelines. If a substance reacts with elemental oxygen, oxygen the element, oxygen all by itself. Oxygen is one of those diatomic elements, and so it'll be O2. But if you see anything reacting with oxygen, a little ding, 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 that's a redox reaction. And I'm going to point out that reactions can be classified as more than one type. Okay, so you don't fit in just one category, just like people. You can say, well, that person is a female. Well, that's one category. But she may also be a mother, and she may also be a daughter and a sister. How can one person be all those things? Well, it's just different ways of classifying people. And we have different ways of classifying reactions, so just because it's a redox reaction doesn't mean it can't be another type as well. So substance reacting with elemental oxygen is a redox reaction. If you have a metal reacting with a nonmetal, a metal element reacting with a nonmetal element, it's a redox reaction. And more generally, if you have one substance that's losing electrons and transferring them to another substance, that's a redox reaction. So I had fun with this one with my students yesterday. Which of these are redox reactions? We'll go through them one at a time. Lithium plus chlorine giving lithium chloride. Does that fit one of those things on the previous slide? Yeah, it does fit. Lithium is a metal, and chlorine is a nonmetal. Metal reacting with a nonmetal. This is a redox reaction. Let's look a little more closely at this to see. So over here, lithium, what charge does a lithium atom have? 0. And the chlorine, what charge does it have as an element in a molecule? It has 0. Both of those are neutral. They don't have charges. When they get together as lithium chloride, this is an ionic compound. What charge does lithium ion have? +1. And chloride is -1. How did lithium become a +1 ion? It lost an electron. Oxidation is loss of electron. Lithium was oxidized. Where did that electron go? The chlorine picked it up. How did chlorine, the element, become chloride, the ion with a -1 charge? It gained an electron. So it was reduced. So that's looking at it more deeply, but you can also just say, oh, metal, nonmetal, they reacted, redox reaction. How about letter B? Aluminum plus tin ions going to aluminum ions plus tin. I've got one no. Yes. Change to a yes. This is a redox reaction. Why? How did aluminum, an element with 0 charge, become an ion? It lost electrons. So this is the last statement in that list. In general, if you have a substance transferring electrons to another substance, it's a redox reaction. So here we have aluminum losing electrons and tin gaining electrons. How about letter C? Is that a redox reaction? Does it fit any of those categories? No, it doesn't. There's not a metal reacting with a nonmetal. We have 2 ionic compounds reacting. Do we have anything gaining or losing electrons? Well, that might not really be obvious. We'll look at that in a minute. Do we have anything reacting with oxygen? No. This is a precipitation reaction. Over here, starting out, lead is 2+, and nitrate is -1, like it always is. And the lithium chloride is Li+ and Cl-. And over here, we've got Pb2+, and Cl- and Li+ and NO3-. Did any of those ions change? No, they just combined differently. So lead and nitrate went to the party together. Lithium and chloride went to the party together. They're friends, but they're not that crazy about each other. But then lead and chloride met at this party, and they're like, oh my goodness, this is this person's awesome, and they precipitated. Okay, there was chemistry there. They formed a solid. So yes, something changed. There's a chemical reaction here, and poor lithium and nitrate are just left kind of hanging at the party. But nothing changed electrons. Nothing gave up electrons. Nothing gained electrons. So it's not a redox reaction. It's a chemical reaction, but it's not a redox reaction. How about the last one? Carbon plus oxygen to yield carbon dioxide. Is that a redox reaction? let's go back. I'm going to lose all my answers, but let's go back to this. What's the first one say? A substance reacts with elemental oxygen. That's what's happening in that bottom one, right? So, whoops. So those were redox, and this is also a redox. Here we have a substance, carbon, reacting with elemental oxygen. That's a redox reaction. And I could explain it to you why it is, but it would take a long time, and we don't need to know that right now. Any questions? So that list on the previous slide is something you need to become familiar with. Again, is this a critical concept? No, it's not a critical concept. Combustion reactions. So combustion reactions are a type of redox reactions. Some redox reactions are combustion reactions, not all. But all combustion reactions are redox reactions. So it's a subcategory. Combustion reactions are when you have a substance reacting with oxygen, and it's going to form one or more oxygen-containing compounds. Often that will include water. Combustion reactions are exothermic. Why do we burn natural gas on the stove or in a Bunsen burner? Because we want to make the room cold? No, because we want heat. It's an exothermic reaction. It generates a lot of heat. If you're burning things that contain just carbon and hydrogen, or carbon, hydrogen, and carbon, hydrogen, and oxygen, you're going to end up with the products being carbon dioxide and water. And that's something you kind of have to just remember. And that's the only sort of combustion reaction that you'll be expected to predict products of. So let's write a balanced equation for the combustion of liquid pentane. The formula is given to you because there's no way you would know what that is. So liquid pentane, C5, that's awfully small, C5, H12, and we're told that it's a liquid, so we should write that down. A combustion reaction. Combustion is burning. What do you need present for something to burn? You need oxygen. Okay, we talked about using the fire blanket during our lab safety lecture. Why do you put a fire blanket around you if you're on fire? To keep oxygen from getting to the fire. Because if there's no oxygen, the fire goes out. Why do we spray water on something to make the fire go out? Because the water covers it and keeps oxygen from getting in. Same thing with smoke detectors, fire extinguishers. They're going to spread a foam or carbon dioxide and suffocate the fire. When you suffocate, you can't breathe because you don't have any oxygen. Combustion requires oxygen. So the other reactant is oxygen gas. Here we have a reactant that's got carbons and hydrogens only. It's a combustion reaction, and so the products are carbon dioxide, and that's a gas, and water. Now you might want to put liquid as the state for water, right? Because you say, well, at room temperature, water's a liquid. If we're burning something, is it going to be at room temperature? No, it's going to be hot. And so the water's going to be a gas. So I'm telling you that. I don't think it's going to really end up being something that you have to be that concerned about, but it's true. So we have our pentane, and we've got it reacting with oxygen and forming carbon dioxide and water. It's really important to get those formulas correct. Now we need to balance the equation. So we have 5 carbons on the left and only 1 on the right, so I'm going to put a 5 in front of the CO2. Next I'm going to look at the hydrogens, because that oxygen is all by itself there, and so that's a good one to leave for last. 12 hydrogens on the left and only 2 on the right. If I multiply this by 6, so that coefficient that you put in front multiplies everything. Sometimes people say, well, I need to add 10 hydrogens. Well, yeah, you do, but how do you do that? So think of multiplying. Now I've got 12 hydrogens on each side. How many oxygens do I have on the right side? Well, I have 5 CO2s, so that's a total of 10. And I've got 6 waters, so that's a total of 6. So I've got 16 oxygens over there. And they're coming in pairs, so I need 8 of them. These combustion reactions are where you're most likely to encounter an odd-even problem. Like if we needed 15 oxygens and they only came in pairs, that's when we have to double everything. Yes, question?
Where did you get the O2 from?
I got the O2 from knowing that a combustion reaction requires oxygen. A combustion reaction is the reaction of a substance with oxygen. So I'll see you back for lab.